multi-dimensional Taylor's theorem, and the immediate application to optimization. If we're in one variable, back to Calc 1, here's Taylor's theorem, or it's the finite power series, however you learned it. So here we can think of this one variable function as a multivariable function that's acting on a line, like we did with the mean value theorem, or more generally, some multivariable function that's acting on a curve in its domain. So we'll just do R2 again, because once you do 2, then 3 is immediate. Once you got 2 and 3, n is immediate. So we're looking at this kind of situation. Or looking in the graph space. I have a curve in the domain that I'm lifting up into the graph. Take a derivative. Or writing it out component-wise. Where gamma is x of t, y of t. Looking at just the components then, we can do the Calc 1 derivative. Well, we're doing the 3D chain rule, of course, for the first term. Organizing the pieces in a linear algebra friendly way. I have this matrix. I'm looking at the quadratic form associated with this matrix. And then our standard matrix vector product for the derivative. So we have a new term. Call it d squared, and our familiar term, the differential. So let's look at this d squared term again. My differential I can identify with a point in R2, and so I can think of it as a R2 to R2 mapping. Thinking of it that way, then I just take the differential, which gives me the differential of each component, and I have a component-wise differentials giving me the matrix. Or I can think of the differential as going to a point and use the point vector isomorphism, and then take the differential. So it's the tangent vectors are the columns. And I get the same matrix. So whichever way you want to think about it, it's consistent with the derivation we just did. But in both cases, we're going to a 2x2 matrix valued function. Now for optimization, back to Calc 1, if I have a one variable function, I have sufficient conditions for minimums and maximums using the second derivative. And now we just compute. We want the derivative to be 0 at a critical point. So looking at the picture, there's our critical point. Which is lifted up into a max or a min situation. So we want the critical point to be invariant under the curve choice. So we need the differential at that point to be 0. So there's a specific t value. That specific t value then we test in the second derivative. And here becomes our second derivative test for multivariable functions. We look at the quadratic form associated with the matrix. And if that quadratic form is positive definite, which means it's a positive number for all vector inputs, or if it's negative definite, a negative number for all vector inputs.